Designing a molecule that binds to a disease target is only half the battle in drug discovery. To actually do its job, that drug first has to survive a brutal physical journey, crossing the cell's lipid membrane. Membrane permeability is the critical physical metric that dictates whether our molecule will actually enter the cell or just wash away. To measure this property computationally, you might think we could just drop a digital drug molecule next to a virtual membrane, start a standard molecular dynamics simulation, and watch it. But biological membranes are dense walls of lipids. The outer head groups are friendly to water, but the inner tails form a hydrophobic core that repels foreign molecules, creating a massive energetic barrier to entry. In reality, a drug might bump against that barrier for milliseconds before successfully crossing. But our computers calculate molecular movements in femtoseconds, millionths of a billionth of a second. Waiting for a random, natural crossing event in a standard simulation is a timescale trap. It would take a supercomputer centuries to observe a single molecule squeeze through, which means we have to actively force the molecule through the membrane to measure it. To bypass this trap, researchers use steered molecular dynamics, which acts like a microscopic tow truck for the molecule. We start by taking the drug molecule and placing it directly into the center of the lipid bilayer, then attaching a virtual spring to it. We apply an external force to that spring, pulling the molecule through the lipid tails and into the surrounding water to establish an initial pathway. Because this rapid pulling is a non-equilibrium state, the resulting data is chaotic and noisy. It's a starting point, but it isn't accurate enough to predict real-world behavior. To fix this, we use umbrella sampling. We slice the vertical path into evenly spaced windows along the z-axis. A molecule snapshot is placed in each window, tethered by a harmonic potential, the umbrella, restraining its movement to that single slice. These umbrella tethers force the computer to spend its computation time on the high-energy, uncomfortable regions of the membrane that the drug would otherwise instantly flee from. The output is a series of overlapping bell curves, histograms tracking how the molecule jiggles within its specific window. But these distributions are flawed. They are artificially compressed by the virtual springs holding the molecule in place. To solve this bias, we use a mathematical translator called the Weighted Histogram Analysis Method, or WHAM. WHAM analyzes the overlapping sections between the windows and systematically strips away the influence of the virtual springs. This vital post-processing step stitches dozens of disconnected artificial simulations into one mathematically pure, continuous dataset. The final result of the WHAM calculation is a smooth, continuous curve mapped directly over the membrane's geography. This is the potential of mean force, the definitive free energy profile of the drug's journey through the bilayer. The highest peak on this curve represents the maximum energetic resistance the membrane exerts against the drug. By calculating the exact height of this peak, a computational chemist can determine if a drug's chemical structure needs to be adjusted to lower that barrier, providing a quantitative way to rank different drug candidates. This pipeline allows researchers to screen and refine drug permeability on a screen, helping them identify the most promising molecules to prioritize for synthesis and physical lab testing.